All right, I just want to quickly run through the basic differences between a series and a parallel circuit because you're going to be having to draw those today. So it's important that you know some of these differences. We will add to the differences as we learn more about current and resistance and whatnot. But for now, we're just going to do some basic how to set up and draw these guys. So the first idea would be that if you are in a series circuit, like this one over here, got yourself a power source, you got your wires, and in this case, we've got a light bulb and then another light bulb. If you notice, there's actually only one pathway for the electrons to follow. So you're going to start off at the negative terminal, and this is the positive terminal here. The electrons are going to move, going to have to pass through this light bulb. Then they'll have to pass through this light bulb. So there really is only one pathway for these electrons to follow. Whereas if you go over here to the parallel circuit, when you leave the battery, they could go all the way around in that pathway, or they can take a detour and go through this light bulb. So you can see that there are actually two different pathways for the electrons to travel. That's going to make a difference between what happens with voltage and what happens with the current, but we'll talk about current. Let's talk about voltage first. So if they are going across the battery like they are in the parallel circuit here, let's say that in my battery, let's say I've got a 12-volt battery, and then let's say that these lights are exactly the same in their voltage. When I go around and I am using, if I'm going and I'm going through the voltage here, this light bulb and this light bulb are going to share that voltage. So if they are the exact same type of light bulb, then they'll use the exact same amount of electricity, and in that case I can expect to split the voltage evenly between them so that this light bulb will be 6 volts and this light bulb will be 6 volts. We would say that this would be, we would call this VT for total, and we would call this V1 and V2 for the voltages of those particular light bulbs. So then we would say that the total voltage is equal to the voltage of light bulb 1 plus the voltage of light bulb 2, which means we've got 6 volts plus 6 volts. So the total voltage is equal to 12 volts. All right. Now when we look over at the parallel circuit, a little bit of a different story. Now we've got the separate pathways so that each of the light bulbs has its own pathway. So that flow, that current, that electrical pressure is full volume in this circuit and full volume in this circuit. So again, if we had the same battery, the 12-volt battery, we would have 12 volts here, but this would have equal access to the battery that this guy would have. There is no sharing of the voltage. So in this case, in a parallel circuit, we would say that VT, or V total, is equal to V1, which is equal to V2. No sharing. So the total voltage then would be equal to the 12 volts and equal to the 12 volts from each one of those. Okay? No sharing of the voltage in those particular ones. Now because of that, we go back to the series. Because of that fact, when you have so now let's go back to the series. If I was to add a light bulb into this thing here, you can imagine that putting another light bulb in would mean that I'd have to share the voltage even further for these light bulbs. Okay, so let's say that I did that. Let's draw ourselves that circuit again, but we will do it with a third light bulb in there. So here's what would happen. You would have your So here now we've got a new series circuit. Now we've added a third light bulb in there. We still had originally 12 volts here, But now we've got it shared between 3 equal size light bulbs. So that means that 12 divided by 3, I'd have 4 volts here, 4 volts here, and 4 volts here. So that each of the bulbs will add up to 12. Well, if that's the case, then each of the bulbs are going to be dimmer. Dimmer because there's less voltage available to actually light up that particular light bulb. So again, if you look back up at the top here, so again, if you have a look at the top here, we've got one battery with 2 light bulbs, so we can have 6 volts each, but we only have one battery here, and each of the 3 light bulbs can only have 4 volts. 6 volts is a lot brighter than 4 volts. Okay, so that's why adding more lights, you're going to get dimmer because of the shared voltage between all of those lights. Now we're adding, in the parallel circuit, we've added a 3rd light bulb. So here we started off with our 12 volts, but on this pathway here, but this guy has its own pathway, so it's going to have full 12 volts. This guy has its own pathway, so it's got full 12 volts. And then the 3rd light bulb has its own pathway, so it's going to get the full 12 volts as well. There's no sharing. When you have a parallel circuit, the total voltage is the same for every branch in the pathway. Now that would be a little bit different if we had a combination circuit. Let's say that somewhere along this pathway here, let's say I added a light bulb. Well, in that case, then I would have some shared pathway. So this guy would still have its own path, that's 12 volts. This one would have its own path, 12 volts. But in the last pathway, there's 2 light bulbs sharing the voltage, so they would be 6 each. So we have our 12 volts, 12 volts, and then 6 volts and 6 volts. So you would expect then that for these bulbs here, these guys would have full brightness, and then these guys would be dim. Okay, and again, that's because these guys are in a perfectly parallel pathway to the battery, whereas these 2 light bulbs, while they are in parallel to this guy and this guy, they are in their own series circuit. So they will share. When you're in series, you share. When you are in parallel, you have full voltage, therefore full brightness and full access to the electricity. So now let's chat about current. Now, if you were to actually measure the current, which again we'll talk about in more detail in a different lesson so you have a better understanding of what it is. It's basically the flow, the actual physical flow of those electrons. It's going to be the same at every single point in the circuit. So if I was to measure in this part of the wire right here, I would get the exact same reading as I get here, as I get here, as I get here. It would all be the exact same. And I would do that, measure that, using something called an ammeter. And you actually need to put the ammeter into the circuit. So you can put an ammeter there. You could do it over here at a separate time. I can measure over here, and I could measure over here. It doesn't matter what part of the wire. I'm going to make sure that ammeters make sure that your ammeters are added in series because you want to measure the current that's flowing through that wire. Okay, so must be in the pathway. So you would take a connection, you'd break that wire there, and you put it on the other side of the ammeter. Okay. What would you see? Well, if we're talking in terms of the numbers that you'd see, let's say that we started off with 3 amps for the value of our battery. Okay, and we knew that because when we used this ammeter, it tested as 3 amps. When we use this ammeter, it tested as 3 amps. Okay. When we tested over here, it was also 3 amps. When we tested over here, it was also 3 amps because it is the same at every point in the circuit if it's a series circuit. Now when we go over here and we're looking at a parallel circuit, when the energy goes out and it goes to this unique branch, we're going to get a different reading because as the electrons are flowing, keep in mind that current is a measure of the charge moving past a point in a second. When the current is flowing here, it has to divide and go down the 2 branches. So some of the electrons will take this pathway and then the rest will continue this way. Then I'll lose some more as they split down that pathway, and so on, so that the current itself flows down different pathways. It will get divided. So the current that I'm going to measure, let's just put my ammeters in quickly. If I put an ammeter in here versus an ammeter in this unique path, in this unique path, and in this unique path, or even in this path over here, when I go to measure with this ammeter, I'm going to see that if I have a battery with 3 amps, I'll measure 3 amps in the unique pathway. Unique pathway meaning the shared pathway that everybody has access here. So as I flow through, I have 3 amps there. But as I come here, I branch off. And let's say all the light bulbs are exactly the same. You can already see, I hope, that if I'm sharing it, let's say I get 1 amp here, then it continues. I would use up 1 amp here, and it continues, and I'd use up 1 amp here. And then when they come back together, I would get more and more current as I was flowing back. Okay? And that 1 amp again would be measured by these ammeters. I should have put them here. So now if I was to take the measured readings of the amperes in each of the sections of this particular circuit, if I had 3 amps here at flowing out of the battery, coming out of the battery here, then when it hits this section here and it can branch, the current can either flow in this direction towards this light bulb, or continue on towards this light bulb, or even continue on towards this light bulb. So that when I actually measure the current that is flowing through this portion, okay, I may only actually get 1 amp rather than the full 3. Same thing over here. If the light bulbs are the same, they'll use the same amount of current because they've got their own unique needs. Now when it comes all back together again, if I was to measure here again, because I've got this guy, and this guy flowing back together again, I'm going to have 3 amps on the way back into the battery. So 3 amps coming out, but being split between 3 amps coming out, but being split between the 3 lights, and then flowing back in together for complete current on the way back. If you want another way to visualize this, you could think about it as water flowing through a bunch of different tributaries or rivers. Let me show you. So here we have an example of another way to picture the current flowing. Let's say that our source, let's say that each one of these little pathways here, the different colors, represent a different amp or different source of the current. So it's all coming out of our original power source, but we've got 3 different pathways for the current to flow. Okay? I hope you can see right away that if I was to measure anywhere near the source in this first pathway here along the source, you can see that it's 3 wide. So in our little symbol case, we're saying that this is 3 amps at this particular location, 3 amps if I measured over here. But if I was to measure in this location, there would only be 1 amp. This location is 1 amp, this location is 1 amp, or if I measured on the other side of the load, it would only be 1 amp, because, for example, in this outside circuit, in this entire outside circuit, there is only 1 amp available and flowing through it. Okay? But when you come back together now in this section, now you've got this guy plus this guy, I've got a 2 amp service. And then over here, I've got myself back to being a 3 amp service as I head back towards the battery. So the current in each branch, really important you memorize this, the current in each branch is less than the current through the power source because the current gets shared. Okay? Current gets shared between each of the loads because each load is using part of that current to run its little machinery, whatever it's going to be, whether it's going to be a light bulb or whether it's going to be a motor or whatever. Alrighty? So there's some really important differences that'll help you to finish today's lesson. Just move on to the next lesson video and you should be good to go. Just a final thought. Now these loads that we just mentioned, they're actually resisting the electron flow. That's why you see the current when it flows through. Just as a final thought, you're going to see that the loads that we've just been discussing are going to resist electron flow and that those charges are going to lose energy. But the current that is before the load, there's the load using the current. The current before the load will be exactly the same as the current after the load. So when we're measuring current here in this pathway or here in this pathway, we should still get the exact same current reading on either side. And just a reminder that the resistor symbol for circuits will be these mountain peaks. You can draw it with a single mountain peak in the middle, or 2 mountain peaks in the middle, or 3 or 4. It doesn't really matter. There doesn't seem to be any consistency, but at least 1 or 2 in the middle is a good plan for your resistor symbol. And this is just showing that the load, a resistor is considered a load, that the load is slowing down the current pathway. It's kind of like it's taking a longer route. All right.